Hello, and welcome to this video lesson on model selection. Unfortunately, it has been proven by two gentlemen named Wolpert and Macready in their no free lunch theorem that there is nothing like a perfect model for all data sets. So you'll need to figure out what models are working better for your particular problem versus others. Picking the right model for your data set, used case, and machine learning problem is a challenging task when you get into this the first time, but luckily, we at RapidMiner are here to help. Your first step should be to consider which of the main task buckets you're in, because if you know that, then you can already eliminate a number of learning algorithms. You have a classification problem if your question is this A or B? Will this be A or B? We're looking at regression with the question, how much or how many? How many will happen? The question for clustering problem is, how is this organized? What belongs to each other? Associations and correlations are used to answer questions like, what happens together? What changes together? And finally, if your question to answer is this weird? Then you're in the area of anomaly detection. In this video, we're looking at the most common machine learning task, which is classification. And now that we know our type of task, we want to identify which subset of models is relevant to us. We've developed a handy tool for you, which will give you the answer, but before we show you that, let's look at the data which we're using first, because we'll need that information to adjust the tool. For many models, certain data types, like for example, categorical information, is not suitable, so that will help us to further narrow down our options. Okay, so we open our O5 cross-validation process and inspect it. The first operator retrieves customer data, and the second filters it to make sure we only have examples with a valid entry in our churn column, which is our label. To look at our data after these two steps, let's set a breakpoint to pause the process execution once we started it. We can do this through the right mouse button and then select Breakpoint After. Later, you'll probably use the F7 key to set and remove breakpoints, much like I will now hit F11 to run the process. Now we are presented with our data and we see that we have our churn, gender, and payment method data in form of categorical or binary data, and age and last transaction are numerical attributes. It's also of note that we don't have any missing values in any of the attributes. Since we're using an example set to demo things, we have just a few attributes and less than 1,000 examples. This is especially important together with the data types, as some learning algorithms may take very long to calculate in case you have many of either one or both. Before we move on, I want to point you quickly to the indication that we're now really in the middle of the process at our breakpoint. See up here? The Run Process button has changed and now allows us to resume the process execution. However, we will just stop it and then return to the design view as we've completed our data review. So let's also remove the breakpoint. Now we're ready to use the little helper tool. You can find it at http://mod.rapidminer.com. As I start filling in the information, you'll see how the list of applicable models changes. Okay, we have all the three column types mentioned here. Our target, or as we call it at RapidMiner, label, is binary. Rows and columns, we have just very few as mentioned before, so we can get by with the default settings. Okay, and now we have a selection of what our starting subset of models is in our area of interest, which is called here predictive. On the right-hand side, we also see what the RapidMiner user community uses most. These numbers are based on our Wisdom of the Crowds database. Further, we see some warnings that we should be considering on memory usage for random forest, KNN, and rule induction. Since we have a small example set, we won't need to worry about that. Now let's be bold and let's try to find the best of our 5 most frequently used algorithms displayed here. Instead of going into our cross-validation operator and swapping them one by one while writing down the accuracies, we will use the much more convenient compare rocks operator. However, first, let's save our process as O6 model selection. Now we will disable the cross-validation and we'll drag and drop the compare rocks operator into the process panel. When you select it, you see the option to change the number of folds of a cross-validation, or the split ratio to be used to create a training and test set. So in essence, this operator loops over every algorithm it contains to determine accuracies. And you won't need to worry about the training error which we mentioned in the testing a model video, because RapidMiner will automatically perform a cross-validation. Or, if you set the cross-validation to the value -1, it will perform a split validation. Through the magic of video editing, we will set up the compare rocks operator with our 5 pre-selected machine learning algorithms quickly. You can see an exclamation mark on the random forest operator, and when we click on it, we see that it is not ready to handle missing values. In a different scenario, we could apply a quick fix to make sure missing values are handled, but since we know that our data has been filtered to have no missing, we can ignore the message. Consequently, we're now ready to run our model comparison. And here's our result, which is called a rock graph. In the rock graph, the true positive rate is plotted on the y-axis, and the false positive rate is plotted on the x-axis. But where do we get these curves from? Let's take a step back and see what we've been doing before. So we reactivate our cross-validation, which has a decision tree inside, and we run things again. The output of our cross-validation is the accuracy and a confusion matrix, which we explain in the Validating a Model video. The true positive rate is now the number of positives, correctly classified and divided by the number of total positives. The false positives rate is accordingly the number of negatives incorrectly classified, divided by the total number of negatives. The false positive rate is also called false alarm rate, and the true positive rate is also known as hit rate. Now these terms give us a good indication about the background of ROC graphs. ROC stands for Receiver Operator Characteristics, and was established during World War II to describe the performance of the people supervising and interpreting the signals on the radar displays. Now let's look at a blank ROC graph with hit rate on the y-axis and false alarm rate on the x-axis. Operating stuff which had an as good hit rate as false alarm rate are as useful as a coin when decided if measures were to be taken when a signal appeared on the radar screen. In the upper right or lower left, we would see extreme examples of an operator who never triggered an alarm, and therefore had also a small false alarm rate, or one who would always trigger an alarm and therefore would never miss an actual true case, but produced a lot of false alarms. Neither of those is useful. The best receiver operators had a very high hit rate and a very small false alarm rate. The same approach is true for our classification algorithms. One thing which is still to be explained is how do we get from a ROC point characteristic, which we can calculate from our confusion matrix, to a curve. For that, we have to extract the confidence for each prediction made by our classification algorithms. The confidence is similar to the probability that the predicted class will actually be correct, and therefore it tells us how sure the model is with its prediction. In RapidMiner, we can retrieve those confidence values from the performance operators. Make sure to connect these to a results port so we get an output. Now, as we run the process again, you can see the confidences displayed. If we rank them, you can see that the prediction changes for those examples with confidences lower or higher than 0.5. This is our decision threshold, which seems intuitively reasonable. However, in some scenarios, we want to adjust this threshold to adjust our classification model. For example, in cases where we're testing for an indicator for cancer, we maybe want any example which even has a small probability to be flagged positive. Or in cases where we're screening our customers for upsell, we only want those flagged as interesting, where we really have a high probability to land a deal, as otherwise we will overload our sales team and waste their time. So by varying the thresholds, we are in fact influencing the decision if an example is flagged as a positive or a negative case. Therefore, we also generate a new confusion matrix with every variation in the threshold, and in turn get a new pair of true positive and false positive rates, resulting in different points on our ROC graph, which we can connect to draw our ROC curve. Now, going back to our output of the compare ROC operator, we can say that the models with ROC curves further to the upper left are the better ones. However, the final model selection for you is also dependent on the preference, if you're looking at a more conservative or more liberal classifier. In this video, we only compared unoptimized models with each other, but often the performance can be drastically improved if you change the modeling parameters. In another video, we will show you how you can do such an optimization in RapidMiner. Thank you very much for watching.